I'm delighted to present Roland Weigand from the European Space Agency. Before working in the European Space Agency, he used to work for Infineon Technologies, designing ASIC chips. And well, we are all looking forward to what he's going to tell us about RISC-V as a rising star in space. Thank you, Roland.
Okay, thank you. Thanks for the introduction. Thanks for the introduction, and thanks for having me here. I'm very glad to give this talk. And so my talk is about RISC-V in space and what we're doing and why we're doing that. So in first place, I would like to talk a bit about the constraints of doing ASIC design, chip design, and in particular microprocessors in space. Now, in first place, we have the reliability constraints. Obviously, radiation is one of the most prominent things, total ionizing dose, single event effects. We can use commercial chips, and that's being done in the constellations. On Ariane 6, they're also using commercial devices a lot. It requires thorough testing, system-level mitigation, redundancy at device level. But we also like to do custom design, and then we have to do mitigation by design, so-called rad-hard by design. We have other constraints. It's not only radiation. We have temperature. Satellite, if it's in the sun, it's getting very hot. If it's off the sun, it's getting very cold. So we try to specify a temperature range -55 to +125. We get all the problems associated to that, dilatation, affecting the interconnect, time enclosure in such a huge temperature range is also a challenge at design. The lifetime is also an issue. We get the vibration at launch, strong vibration, relatively low frequency spectrum. There's also stress on interconnect, bonding wires and so on. We have outgassing in vacuum causing in turn contamination of sensors. And the tin whiskers is a very peculiar thing. You see it on the picture. And that requires that we have to go for leaded soldering, leaded interconnect, and that is increasingly difficult because on Earth the leaded supply chain is disappearing, it's forbidden. Then we have the lifetime. Some of our satellites, they remain in orbit for 20 years in the telecom satellites. There's exceptions even longer. That's much larger than, the mobile phone. For how long do you keep it? 3, 5 years? And we cannot do any repair in space. Okay, so how do we tackle that? Radiation hardening. Well, we can do library design. We try doing dedicated standard cell libraries for our design. Typically what happens, we have particles like neutrons, heavy ions, protons. When they come into the semiconductor, they generate charges. The charges pop up as glitches in the circuit. Those glitches, if they're in the combinatorial logic, they're usually harmless in synchronous logic unless they're being latched into the flip-flops. So we have to do something. We can use glitch filters, design dedicated library cells, and use them in our circuits. We have the single event upsets if we hit directly a flip-flop. Flip-flop is a cross-coupled inverter. We can add redundancy, like you see here. The dice cell, we double the number of inverters. In addition, the feedback is going to both directions. If you take any of those nodes, A, B, C, D, in that circuit, and you flip the nodes, the flip-flop will keep its overall state. It will go back to its original state. But we have a high penalty. It's an area overhead of 2 to 3 times. We also see timing and power overhead. That penalty is definitely too high for the bulk memories, for the RAMs on our chips, for the caches and register files. If we cannot make a dedicated rad-hard library, then we can use a commercial standard cell library by using TMR, triple modular redundancy. We triple all the flip-flops and do majority voting of the outputs. We still have the problem that glitches in combinatorial logic can be latched into the 3 flip-flops at a time, then we still generate an upset. We can in addition mitigate that by putting a skew on the 3 clocks going to the 3 flip-flops, such that if an SET pulse, a transient pulse, arrives at the data inputs of the flip-flops, it would be latched only by one of the flip-flops at a time, so it could be corrected by the following majority voting. This has been done, it's flying. We have done a single core SPARC. It has been our workhorse on our missions for many years. It has flown to the backside of the moon. The TMR penalty is also high, certainly too high for the memories. So for the memories, we want to use error correcting codes, typically single error correction, double error detection. So that's relatively easy to implement. We have a timing penalty. But there's one thing to be considered. We can generate the parity when we write to the memory. We correct on the fly when we read out the memory, but the error remains in the memory. So what do we do about that? The next error we get in the same memory word will be then a accumulated double error, and then we cannot correct anymore. So we have to write back to the memory. And that means we have to convince the processor to do something in addition. So when we detect an error, we have to insert a cycle to write back and to update the memory with a corrected memory word. We have other means when the memory is already duplicated, like caches. Right through cache, you always have an external copy of the same data. Then we can protect by simple parity. But still, we have to do something about correcting for that. It means for a cache, for example, we have to generate a cache miss such that correct data is fetched back into the cache. So what we need to do and what we want to do is modifications to the control of the pipelines, in the pipelines of our processors or the cache controllers. Here we have a case, I think, for openness, for open standards, because this is typically impossible with proprietary ISAs and proprietary IP cores. We also have functional constraints. We have timing critical functions, the platform control, the launchers, and our first multi-core chips, people used them in single-core mode because they were afraid, for example, of the multi-core interference. We have also seen people, when caches were introduced in the 90s or beginning of the 2000s, we have people switching off the caches because they were obsessed by the predictability. Today, we're increasingly looking into mixed criticality software. It's a bit similar to what we have seen on Tuesday from the automotive world. We have the hard real-time and critical safety functions, and at the same time, we have the multimedia running, and we also have cases where we want to run mixed criticality on the same processor. So we're looking for hypervisors and time and space partitioning. We also have dedicated peripherals. We have a lot of interfaces derived from commercial or automotive or military world, but sometimes with additional requirements. So we have our own IP. So that's also motivation for us to design our own chips. Okay, now talking about economics, because it's not only about technology. We're in a very peculiar situation. We have very low part counts. In the past, we have seen ASICs being made for a single mission, for a single project, where you make an ASIC and you produce, and in the end, you need just a handful of them in your mission. Today, this is disappearing. We're only making standard products, but then still we count them in thousands or 10,000s only. We also have long product cycles. I always say 10 plus 10 plus 10, 10 years development. We try to improve that, of course. 10 years apart is on sale, and then it's still 10 years in use by the mission, so it has to be supported still. So life cycle can be 30 years. The supply chain is expensive because of all the constraints. I mentioned that, ceramic packaging, the qualification. We have destructive testing during qualification. So it means the recurrent prices are dominated by the back-end packaging, testing, assembly, and so on. Prices like 50K euro per flight part are nothing unusual, figure out. Saying that we have low part counts, but we have relatively high part prices means you can make profit in that business. But getting the attention of the commercial players in the semiconductor world is extremely difficult. TSMC is producing 12 million wafers a year. If we come here and we say, oh, I want to order 12 wafers, half a lot, they say, go home. So it's kind of difficult to get the attention The IP providers, they're typically looking for a short to medium-term revenue. If we say we want to design in something, but the royalties, you will get them only in 10 years because that's only when we start really selling the flight parts. They are asking for extremely high upfront license fees, which in turn causes a problem with our setup because we're working on public funding and we're always starting with little strokes of funding of memory. We have to prove something, we have to do prototypes, and then it's progressively increased. Generally public funding, we have other constraints, we have expenditure rules like geographic returns. The member states funding us want to see the money flowing back into their countries, which make the selection and forming of consortia sometimes difficult. All this to explain a bit the particular situation, and we're a small community. It's a small world in space. Now, talking about open ISA, because that's what we're here for, general motivation, I would start with something which happened, almost 30 years ago, where ESA has started developing on SPARC, which is similar to RISC-V, an open ISA. The most prominent reason was a non-dependence. It allows for multiple IP sources or own development. Our first implementation was a commercial IP. We bought it from Cyprus. Then own IPs were developed. And as I already mentioned, we want to do modifications of the IP for radiation hardening. So it's difficult with proprietary solutions. So SPARC at the time was selected because it was well established and there was backing in industry and academia. Sun and Fujitsu were still doing high-performance computers at the time. It was stable and reasonably simple, so that's why it was selected. Now, a word about Open ISA. They're not for free. Sometimes I'm a bit in trouble to explain that to our management as well. And they may not even be better than the commercial solutions. An open ISA in first place, it's not an open IP, it's not an open source IP. And even an open source or a free source IP is not for free because then you probably have to spend a fortune on IP validation. But the open ISA, it allows for competition, and we have multiple IP sources and many people in the community developing them, as we see here in this room. That warrants for flexibility and for us, very important, non-dependence. So I mentioned SPARC. 30 years ago we started. They're flying for about 25 years. We're not finished with that. We still have a tape out in the pipeline. Octa-core and 28 nanometer is currently under development. It's in all our missions. I would say it has been very successful. Certainly more than 10,000 flight parts are around. The ecosystem is in place, it's mature, and we still have demand for it. We have still people asking for it because they have legacy software. So why should we change if it works? Well, so why should we go RISC-V? Why not doing SPARC forever? Well, SPARC is obsolete in the commercial world, so the community backing is stop. And we see a lack of developers. People coming from universities don't know it anymore, so sooner or later we have to do something else. So why not proprietary? Well, we can, yes, we do. ARM is flying in space in many instances. And we have Nano Explorers doing Rad-Hard Space FPGA. They have selected ARM for their hard macro processor subsystems in the FPGAs. But as I mentioned, we have the dependency issue, and it's difficult to do IP modifications for specific RAD hardening. So RISC-V, then. Looking into RISC-V, yes, the open ISA, so continuation of the success story, I mentioned that, and the multiple IP sources. Particular interest, of course, is the extensibility. We can use it from low-end to high-performance applications. In particular, I want to point out two things. The hypervisor, I mentioned the mixed practicality. Hardware hypervisor is something extremely useful, which will allow to use unmodified operating systems under a hypervisor. And the vector extension is also something we are currently looking to. Because we also see a demand for high performance and AI applications in space. I'll come to that. We also have a couple of technical features. SPARC had these register windows and the delay slots. We can consider them as obsolete, but okay, small details. And we have this amazing developer community for RISC-V in industry, in academia. There are a couple of challenges as well. RISC-V was relatively recent, not so recent anymore because it was initiated in 2010, but the real popularity started only after 2020. But space is extremely conservative. Software qualification cost is high, people are reluctant to change. I guess it's a bit similar as in automotive. People are still observing, some people are observing. And at ESA we have been late as well, starting it, but we're going fast now. And one of the questions which is always coming back to us, okay, RISC-V, what is the maturity of the IPs you have on the market? How do you prove that? How do you certify that? And that's for us, what I would like to see here is, let's say, compliance tests, also a certification system. In SPARC, that used to exist. It's something we're still missing, so we have to work on that. Talking about the extensions, in first place, I think we're a small community, so we should be extremely careful with custom extensions because we will not have the capacity, we will not have the resources to build the whole ecosystem behind that, the software ecosystem. But even for the official extensions, I'm very happy to see that a lot of extensions have been ratified earlier this year, so that's fantastic. But I would say we're not 100% sure that all of them will really survive on long term in the community and be supported by the compilers and everything. So it's something I would say we have to observe. Now, what are our developments? What are we doing in RISC-V? For space. In first place, we have the chip I already mentioned, octa-core SPARC in 28 nanometers. But actually, this is going to be a dual architecture chip. One chip, both ISA. So the processor cores are duplicated. They're sharing the cache and all the rest, and the L2 cache and all the rest of the system on chip. Only the processor cores are duplicated. You can boot the system either in SPARC mode or in RISC-V mode. That is in first place, it's simply for cost reason. We have a synergy in development cost and in mass manufacturing. 28 is already quite expensive. And it has also the effect of facilitating the transition for our users. We can give to users a board, an eval board, and they can keep running and testing their legacy software while they're also developing new applications for RISC-V. It's just a bootstrap pin and you reboot the thing in the other architecture. That's the idea behind that. So, talking about high-performance computing, well, if I say high-performance computing, you might think about data centers and things like that. It's not what, I don't think that's what we're going to do in space, at least not any soon. Nevertheless, we have increasing performance requirements. Traditionally, what we have been doing is very little. Computing in space, that was for maintaining the platform, attitude and orbit control systems, data handling, but not really processing. Most of the science missions, the scientists, they build their instruments and they want to download all the data acquired by the instruments, by the images, bit by bit. Even compression would be allowed only if it's lossless. But it's changing recently. Why? Because instruments are producing more and more data, the resolutions of the cameras is increasing, whereas the downlink bandwidth is not getting any cheaper or is not really increasing. So we have to do data pre-processing. Also, we have a move to Earth observation. Earth observation is a steeply increasing segment, and that has a different business model, and they want to get useful data. They're not insisting on having petabytes of all data. So we want to do data pre-processing, reduction of this big amount of data, selecting useless and eliminating useless images, for example, things like that. We also have planetary exploration. If you go to Mars, you have a communication delay of 3 to 22 minutes. So if you want to do an operation of a remote-controlled rover by linking down the commands to Earth to a control center and taking a decision and feeding it back to Mars, it will take forever. So you're getting very slow. So we want to have increasing autonomy, and that requires higher performance computing to improve the precision and the mobility, the speed of the rovers, for example. Telecom is also a big push for processing. They want to do software-defined radio. We have digital beamforming. 5G is expanding into space. 5G NTN stands for non-terrestrial networks. So we're going to get processing in there as well. Cryptography should be mentioned as well. Quantum key distribution via space is also an emerging segment. We have many different algorithms, so it's difficult to find a bit, what is the best architecture for each of these applications? We have machine learning, we have filtering, we have FFTs, we have the compression. It's difficult to find a common denominator. What appears to me, what I keep hearing from the experts, is that whatever we want to do, we always end up doing massive parallel multiplication or MAC operations, vector and matrix operations. That's maybe the common denominator. Now, talking about high performance, how could we solve that? Well, the classical GPP, if you try to evaluate architectures, let's say performance and the flexibility against the energy efficiency, then the general purpose processor is really bad because you have to fetch one instruction for each operation. Of course, the most efficient is going to be the ASIC. It will provide high performance, and it can be very efficient because it's custom designed, but it's totally inflexible. You do it once, and then, you cannot really change. Very good scores we see and for FPGAs and the CGRAs, the coarse grain reconfigurable arrays or tiled processor arrays. They're very low power, but there's a but, because they're efficient only if you manage to reach high utilization. If you take a huge FPGA and you use it only for 10%, then you have a big penalty of leakage power. You also depend a lot on the hardware tools, on the design tools. They're very critical for FPGAs, and that's where you see the problems sometimes. And that also applies to the CGRAs, because in the end, mapping an application onto the processor array is also a kind of synthesis and place and route operation, like for FPGA design. Very similar. So we have the two spectrums, and what we believe is that if we start from a general purpose processor and we add parallel instruction extensions, vector instructions, we can improve the efficiency a lot and increase the performance as well, but keep the flexibility to run all kinds of applications, because we cannot make a tape out for each of our applications. We cannot afford that. So here we clearly have a case for RISC-V and RISC-V extension. Where it comes to the next project, currently it is an architectural study. It's a preliminary design, very classical clustered 4x4 core architecture based on Scala Noel 5 cores. We'll try to modify that architecture. Trade-offs will have to be made. In particular, yes, I think we definitely want to have vector extensions there, still parameters to be defined, VLAN, well, which data types to be supported. Are we going to support all the instruction spectrum of RISC-V? A possible change to asymmetric architecture. We see several architecture pulp doing that. PolarFire SoC has a 4+1. NASA microchip HPSC is probably doing 8+4, not completely confirmed. And the biggest challenge is we have to work on the cache and memory architecture, because if we go for parallel processing, we have to make sure that we shuffle the data in and out. Otherwise, our vector units will be idling. And that's the work for the coming couple of years to do. The chip is, for the time being, targeting 7 nanometers, but we first have to see if a 7 nanometer library for space is ready. Okay, talking about NASA, I already mentioned that. It's an interesting case. They started around 2018. We had several presentations. I presented the architecture shown top left based on 8-core A53. That project was stopped. Probably not because of ARM. I understood that the 32 nanometer technology they wanted to use was stopped. So they had to restart and rethink the project. And they opened the trade-off for the ISA trade-off. And they had a parallel studies in 2021. And they ended up, and they gave a contract in 2022, not too long ago, to Microchip. And they're going to use RISC-V cores. So they're going to use Sci5 X280. So that's RISC-V with vector extension. When I heard that, I say, okay, that's great news. It's great news for us because it will also help us to promote the RISC-V in the European space community. Few words on microcontrollers. I'm running out of time. The focus, and we have been doing microcontrollers in various architectures for a long time. We see ARM, we see OpenMSP 430, very old 16-bit architecture. We have SPARC microcontrollers. Here we begin to see a transition to RISC-V as well. Technolution has an IP core. They have ported it to Rad-Hard FPGA. A colleague of mine has done his own RISC-V design. And we're trying to push on that side as well by developing a RISC-V microcontroller IP, which will be available as IP on ISA portfolio for the community for space projects, targeting soft IP on the sometimes relatively small space FPGA and standard microcontrollers. At last, RISC-V is in space already. We have there's a nanosat by University of Maribor in Slovenia that was launched almost a year ago. That is using an OBC with an OL5 soft IP running on a PolarFire FPGA. It's not PolarFire SOC, so it's not a hardcore, it's a soft IP. It's running in space and it's working. There is certainly more use of RISC-V, people having controllers in their FPGAs here and there, and they do not publish it. So it's certainly not the only one. RISC-V is already in space. Trying to conclude, so we have seen the chip design in space is a very specific and very peculiar thing. We have all the constraints, reliability, environmental, radiation, but also different project and cost setup, which makes our lives sometimes very, very difficult. We have been using OpenISA for 30 years, SPARC, and I think we have been happy with that. We have been very successful, but it's coming to an end with SPARC. Keep in mind, OpenISA is not for free. If you want mature IP, there's always a price, and we always have to spend effort on that. The transition to RISC-V for us continues the success we had with SPARC. We see additional value by the RISC-V extensions, the standard ones, the official ones, as I call them. I would recommend our community, at least, being careful with custom extensions. We see a need to have IP certification, and also we have to watch the perennity of the extensions, including the official ones, and the acceptance in the community. So we are busy with RISC-V. We have chips in the pipeline. It's already it's already flying RISC-V, and we also see a need for high performance, and that's maybe surprising, but yeah, there's a pull for that from our applications, and the way forward is to do RVV. Then NASA has decided more or less the same thing, RISC-V with vector extension. So, in summary, RISC-V for us is a great opportunity. I would say it's a rising star, and we're trying to promote the transition to RISC-V, which doesn't prevent people from choosing other architectures. So we have diversity, and that's okay. Thanks a lot.
Thank you for this very interesting talk. We have time for a couple of questions. So I see a couple of them. That one, and then.
I wonder if you have open calls for projects in respect to this RISC-V architecture.
I'm not sure if we have currently an open call. We have had an open call in the past, and this has led to one of those projects. If you're interested, I can give you a link where the calls are being published. There is a website where the open calls are being published. But I can also tell you that a lot of what we're doing is based on direct negotiation, which means that companies seek for support of their own member state, and then we're running activities. So it's not everything is in open calls, but some things are in open calls, and there will certainly be more.
There's another question there.
Hello, is there any value in having different SKUs than the NASA is using at ESA, or would it make more sense just to say for each of these organizations just develops one class, which is then also used by the other?
That would be in an ideal world, yes. In the real world, we have export control, and so there is a strong motivation to do, let's say, dedicated implementation in the different geographical regions of the world. We're not the only ones. Asia is doing their own implementations as well. China, Japan is doing their own implementations. There is some exchange, and luckily we're doing exchange at technology level, at technical level. We have had talks to NASA last year, and I think the year before, about RISC-V, and the conclusion was, yes, we will each go do their own implementation. Also because we want to select suppliers from our own geographical regions. So the US wants to do homeland suppliers, so they chose Sci-5, and we have European IP suppliers and companies. But the conclusion was, yes, if we manage to agree at least on the ISA, we have a big added value, because for the software community, the exchange, technical exchange at conferences and so on, mobility of stuff as well. So, but one implementation for the whole world, I'm afraid it's not going to work, as sad as it might be.
Okay, we have a last question there.
Thank you. During your talk, you talked about the need for certification or standardization. And I was wondering if ESA had any plans to try and launch maybe a standard for qualifying open source hardware, because such a standard might help guide the open source community. I'm thinking in terms of what artifacts you need, what levels of quality you need for an IP to be acceptable for use in space.
We have standards for IC and ASIC and FPGA development, for the development methodology. We also have guidelines for IP development, but they're not specific to open source or open hardware solutions. We begin to look into open hardware as well, but so far there hasn't been any standardization. When I'm talking about certification, it's more about the certification of the compliance to the ISA. That's what I meant with that. But it's maybe a suggestion. Maybe that will happen in the future. Thanks.
Thank you again, Roland.
Yeah, thank you.
So our next speaker is Luca Lingardo from NXP Semiconductors, and he's going to talk about implementation of an edge computer architecture based on a RISC-V core for RFID communication. Hi, Luca. Thank you so much.